Good morning, everyone. So today we will continue our discussion about the noise theorem. So in the previous lecture, we showed two examples about the relation between symmetry and the conservation law. Okay, we showed the first example we showed is the gauge symmetry, and from the gauge symmetry we find the continuity equation, and that continuity equation is exactly the conservation law for charge. Okay, the continuity equation for charge, and it defines for us the charge conservation law. And it defines for us the charge density and the charge current density. Okay. And the second example we demonstrated is the translational symmetry in space and time. Okay. And we showed that if the system is invariant, when we shift the whole system in space or time by some distance, then this is the so-called translational symmetry. And as long as we have translational symmetry, we can define the conservation law for energy, as well as the conservation law for momentum. And the momentum conservation law has three conservation laws for Px, Py, and Pz. Okay. And in general, we can perform the same type of analysis for any continuous theorem, for any continuous symmetry. Okay. And for any continuous symmetry, we can repeat the same analysis, and we will find some corresponding conservation law, some corresponding continuity equation. And this was pointed out by Neuser, and this is known as Neuser's theorem. Okay. So in our lecture, in this course, instead of prove this theorem for any symmetry, we will only focus on the gauge symmetry and the translational symmetry as we demonstrated in the last lecture, in the previous lecture. Okay. But you can repeat the same procedure for any other symmetry. Okay. If you are interested in about the more details, there is a very nice reference, the book Conformal Field Theory, and the section 2.4 and 2.5. There is a very complete and very comprehensive presentation about how to prove this theorem for generic symmetry. There, basically, you can prove, and for any symmetry, you will get eventually some conservation or some continuity equation. Okay, so this is known as this is the fundamental relation between symmetry and the conservation law. Any continuous symmetry gives us continuity equation, and continuity equation gives us a conservation law. Okay. And another important thing, another important concept we demonstrated in the previous lecture is how to write down the conservation law for a continuum system. Okay. So for a continuum system, the conservation law combined with the principle of locality, conservation law combined with the principle of locality, always manifests itself as a continuity equation. Okay. So for any conservation law in a continuum, we need to define two quantities. The first quantity is the conserved quantity density, the density of conserved quantity. For example, charge density, energy density, or momentum density. And in addition to that, we also need to define the corresponding current. Okay. And the continuity equation or conservation law demonstrates itself, manifests itself as this type of equations. The density of the conserved quantity take a time derivative plus the divergence of the corresponding current need to be equal to 0. Okay, and we have showed earlier on this conservation law, say for example for charge density, shows that the total charge for the entire system would always remain the same as long as there are no additional charge flows through the boundary. And similarly, if we define the spatial integral of the energy density, and that quantity gives us total energy, and total continuity equation tells us total energy will be a constant as long as there is no energy flow into the system or flow out of the system through the surface. Okay, and we also showed in the previous lecture for the conserved density and the corresponding current, the current always has one more rank than the corresponding conserved quantity. If the conserved quantity is a 3D scalar, then the current will be a 3D vector. If the conserved quantity is a 3D vector, then the corresponding current will be a 3D rank 2 tensor. It always has one more rank than the corresponding conserved quantity. Okay, so that is what we learned in the previous lecture. Okay. So today we will do two things. In today's lecture, we'll do two things. First of all, we will look at the momentum and energy conservation law a little bit more carefully, and we will rewrite the momentum and energy conservation law in 4-dimensional formula. Okay, because as we learned earlier on in relativistic language, in relativistic theory, energy and momentum should be combined together as one 4-dimensional vector. Okay, so energy is the first component of the vector, and the rest three components are the px, py, and pz correspondingly, respectively. Okay, so energy and momentum should always be written together in the relativistic theory, and thus energy conservation law should also be written in terms of a 4D formula, okay, that is required by the Lorentz symmetry and special relativity. So our first task is to rewrite the energy and momentum conservation law, the same thing we learned before, in a 4D structure. And the second part of today's lecture, we will apply the energy and the momentum conservation law we learned in the previous lecture to E and M field. Okay, and we will utilize the action of E and M field we learned before, and following the same construction to figure out what is energy density, what is current density, etc. for E and M fields. Okay, so let's first look at the energy and momentum conservation law. Okay, so in the last lecture, we showed that from the field theory and the translational symmetry, we can define energy and the momentum conservation law. And the energy conservation law, sorry for that, let me go down a little bit. So the energy conservation law tells us we can define energy density, which we call W. It is this quantity. As long as we know Lagrangian density, we can immediately calculate the energy density for this field. And the energy current density is here. We just need to do this. Okay, so that's energy conservation law. And if we consider translational symmetry in space, we obtain the momentum conservation law for px, py, and pz. Okay, and the momentum density, x component momentum density, y component momentum density, and the z component momentum density forms a 3D vector. We can write down the momentum density vector and this. Okay, and their spatial integral give us momentum. And the momentum density, the momentum current density is a 3x3 matrix, is defined here. We can write it in the 3x3 matrix formula like this. Okay, and the continuity equation for momentum looks like this. Okay, and today we will combine these two formula, this energy and momentum conservation law together into the 4-dimensional formula language. Okay, and as we learned early on, in order to guarantee that our physics stays invariant under Lorentz boost, let's say our physics laws stay the same in different reference frame, we have to be able to write down all physics laws in 4D form. Okay, and with this 4D form, need to match scalar with scalars, vector with vectors, tensor with tensor, etc. So that is what we are going to do in this section first. Okay, so let's start from this formula. Okay, so this formula is actually a formula we learned in the previous lecture. Okay, if we go back a little bit in the previous lecture, okay, when we consider a generic translation in space and time, and we assume that the system has space-time translational symmetry, and at the end of the day, we find that if we want action S to be equal to S prime, this whole thing needs to be equal to 0, and we massage the formula a little bit, and we showed that that means this guy needs to be 0. Okay, and if we want this guy to be 0 for any translation, any epsilon, this whole thing in the square bracket needs to be 0. Okay, and that is where we obtain this formula. That's equation 4.183. This is the equation we learned in the previous lecture. So today we'll start from this formula. Okay, let's go down. Okay, so we'll start from this formula. This is the same formula as the formula I showed you above. That's from the last lecture. Okay, and today the first thing what we will do is we will define what inside this parenthesis as T mu nu. Okay, I'll define this whole thing as T mu nu. Okay, and you may notice that here I played a small trick, or I use a small notation here. I purposely put mu as a superscript, as an upper index, and the nu as a lower index. Okay, I didn't put mu and nu together. One is super index, another is subindex. Okay, the reason I put them in different way is because of following. Is because this T mu mu, okay, if you think about this T mu mu, what it is, it's actually a 4x4 matrix. Mu is 0, 1, 2, 3. Nu is 0, 1, 2, 3. So it's a 4x4 matrix. Okay, so a 4x4 matrix in the earlier lectures, we learned that 4D tensor, 4D rank 2 tensor is a 4x4 matrix. Okay, so T mu mu, this quantity we define here, is very similar to the 4D rank 2 tensor, 4D 4x4 matrix. However, it's not quite a rank 2 tensor. Okay, as we learned early on, what is a rank 2 tensor? So first of all, rank 2 tensor need to be a 4x4 matrix, Okay, so rank 1 tensor is a vector, it's 4 by 1. And the rank 2 tensor is a matrix, it's 4 by 4, as we learned earlier. And more importantly, this 4 by 4 matrix need to follow the following transformation under Lorentz boost. Okay, so under Lorentz boost, suppose M is a rank 2 tensor. Under Lorentz boost, it will become M prime. Okay, and this M prime should be equal to M multiplied by L from the left side and right side transpose of L. And this L is the 4 by 4 matrix of Lorentz boost. Okay, so we learned early on that for let me get my pencil. We learned early on that so for 4D vector, say I have 4D vector, say x. Okay, a 4D vector under Lorentz boost becomes x prime, which equals to Lx. Okay, and this L is a 4 by 4 matrix that gives us Lorentz boost, the same 4 by 4 matrix we use to boost T and X, Y, Z. Okay, so the vector is defined this way, and rank 2 tensor is defined this way. Okay, for rank 2 tensor, we need to multiply L on the left side and L transpose on the other side. Okay, if we look at the T mu nu we defined here, this T mu nu we defined here. Okay, this guy is a 4 by 4 matrix, so in that sense, it's very similar to a 4D tensor. But it's not a 4D tensor. The reason it's not a 4D tensor is because if we perform Lorentz boost, this T mu nu didn't follow the Lorentz boost of the rank 2 tensor. Okay. Under Lorentz boost, this T will become T prime, and T prime is L times T. We multiply L from the left side, that's right. But on the right-hand side, we should multiply L transpose for rank 2 tensor. But for this T matrix, what we need to multiply is the inverse Lorentz boost transpose. Okay, we got the extra inverse. Okay. So left-hand side is Lorentz boost, right-hand side is inverse Lorentz boost. So in this sense, this T is not quite a 4D rank 2 tensor. It's not a 4D rank 2 tensor. For rank 2 tensor, I need L and L transpose on both sides. Here is L and L inverse transpose. Okay. So the mathematical terminology for this matrix is it's a mixed rank 2 tensor. And for the first index, for the first index mu, it's a covariant index, and for the second index nu, it's the opposite way. For the first index mu, it's a contravariant index. We know contravariant follow Lorentz boost. That's why we have Lorentz boost. Okay. But the second index nu is a covariant index, and we know for covariant index, it follows the inverse Lorentz boost. That's why we have the inverse Lorentz boost on the other side of the equation. Okay, so the bottom line, this T matrix is kind of like a tensor, but it's not quite a tensor. Okay, one side of it, one of the index mu, follow the correct tensor behavior, but the other index mu follows the inverse Lorentz boost instead of Lorentz boost. Okay, so it's not quite a tensor. Because this guy is not quite a tensor, we need to make a trick to make it a tensor, make it a rank 2 tensor. And that, it turns out that can be done quite easily by multiplying this T matrix with the inverse of matrix tensor. Okay, so T is a 4 by 4 matrix, we know that. Okay, matrix tensor is also a 4 by 4 matrix. We can take a matrix tensor and the inverse matrix of matrix tensor, and multiply T and G together. T on the left-hand side, G on the right-hand side, multiply them together. When we multiply two 4 by 4 matrix together, we still get a 4 by 4 matrix. And I want to show you, I want to argue that that 4 by 4 matrix is a regular tensor. Okay. Oh, I should emphasize that in our lecture, I will not prove to you this under Lorentz boost, this T matrix behaves like this. Okay. The detailed mathematical calculation is not so important. If you're interested in it, we can talk about this afterwards. But in this lecture, I will skip this detail, just gives you the answer. Okay. So this T matrix follows this transformation. But if we multiply T matrix with the inverse of G, then this will become a regular rank 2 tensor. And under Lorentz boost, it will behave like a regular rank 2 tensor. Okay, I will not prove to you why it is this, but I will just give you the conclusion. This is what happened with this matrix. Okay. Okay. So anyway, so this is a way to get a regular rank 2 tensor. Okay. So we need to modify this guy a little bit. So this guy we call it T, with one upper index and one lower index. But that is not what we typically use. What we typically use is slightly different matrix. This T matrix multiplied by the G inverse matrix. Okay. And we can write down the component of this new matrix. Okay, so for this new matrix, T times G inverse, I will call it T mu nu with mu nu both as upper indices. Okay, and our old matrix, the original matrix we defined here, I will call it T mu nu, one upper index and one lower index. Okay, and for G inverse matrix, one convention for special and general relativity is that for the G inverse matrix, we also call it a G, but we use upper index. Okay, so alpha and nu, we put it as higher super indices. Upper super indices of G means this is actually the G inverse matrix. Lower indices means it's G, it's a matrix tensor. Okay, so this is not important. There's nothing fundamental from the physics side. It's just a mathematical convention. Okay, so anyway, so this new T matrix we utilize is actually this guy. It is my old T matrix multiplied with the inverse of G matrix. Okay, and another small thing I want to mention is that in special relativity, this is our G matrix, and you can easily verify that in special relativity, G inverse and G actually are the same matrix. Okay, so it doesn't really matter whether you multiply G or G inverse here because they are the same matrix. However, if you are dealing with special relativity, G and G inverse would in general not be the same matrix. And there you will notice that you have to multiply G inverse matrix. Okay, so for us, it doesn't really matter. You can do G matrix or G inverse matrix, doesn't really matter. But for special relativity, you need to be very careful. You have to multiply G inverse, not G. Okay, anyway, instead of this T matrix, we will utilize this T matrix with both super indices. Okay, and that T matrix is what we are going to use to define our four-dimensional energy and momentum conservation. Okay, and this new T matrix is our old T matrix times the matrix tensor. Okay, and actually the inverse of matrix tensor. And our old T matrix is this guy. Okay, and we will multiply it with G alpha nu. Okay, and the super index means it's inverse of G. It doesn't really matter because G inverse and G are the same matrix. Okay, so we can multiply this G mu nu inside my parentheses to get two terms. Okay, and in order to make the formula a little bit more compact, typically people introduce a convention where people combine these two terms together. Okay, we have a G multiplied by derivative. Okay, so when we multiply this G and derivative together, typically people call this whole thing partial nu. Okay, so this whole thing multiplied together is called partial nu, and this nu has a higher index. Okay, notice that partial alpha, the alpha is a lower index, but when it multiplied together with G mu alpha nu, we call it the whole thing partial nu, with nu as a higher index. Okay, and this is what people utilize in the covariant and the contravariant notation. Okay, it's nothing fundamental, it's just a notation. With the upper index derivative means the multiplication of these two. Okay, just a convention. Okay. And in this convention, if we want to write down what is a partial nu, the first component or the zero component of partial nu is 1 over c partial t. The second component is minus partial x. The next component is minus partial y. The next component is minus partial z. And the minus sign here comes from the G inverse matrix. For the G inverse matrix, we have 3 minus 1. That gives us this 3 minus n. Okay. So again, it's nothing fundamental, just a convention. With this convention, we can combine this G and the partial derivative together as one partial derivative with upper index. Okay, so that makes the formula a little bit more compact. And another thing we utilize is delta times G. Okay, for the second term, we have delta times G. Here, delta is a chronic delta. Chronic delta means alpha and the mu must be equal to each other. So alpha is actually mu. So we can combine these two terms together, delta and G together as one G, and replace alpha with mu. So it's G mu mu. Okay, so that's the second term. We can make it a little bit more compact. And this is a T mu nu matrix that we are going to use. And this matrix, we can show that it's a rank 2 tensor. And this rank 2 tensor has a name. It is called the energy momentum tensor. Okay. It is also known as the stress energy tensor or stress energy momentum tensor. Okay. And this tensor is what we need to define a 4D formula for the energy and momentum conservation. Okay, so that is the definition of the energy momentum tensor. It's pretty much the same thing as what we have in this formula, except that we multiplied it with the inverse G matrix. Okay, anyway, so for we know that from the original formula, from the translation symmetry, we know our old T matrix, one upper index, one lower index, obeys the equation partial mu, T mu nu equals 0. Okay, so this is what we know. This is actually this equation. Okay, I just gave this guy a name, call it T mu nu. Okay, so for the T mu nu, our old T mu nu, we know it obeys this equation. For the new T matrix, T mu nu with both upper indices, it obeys exactly the same equation. Okay, the reason for that is because we can multiply a G for this equation. We can multiply inverse G for this equation. And because G matrix is constant, it's a constant matrix, I can multiply. So if partial T equals 0, then partial T, G inverse, must also equal 0, because G is just an inverse. It's just a constant matrix. G and G inverse is constant matrix, independent operation. Okay, so which means our new T matrix obeys exactly the same equation. Okay, so this new T matrix we define obeys the same equation as the old T matrix, but it has an advantage. The advantage is this new T matrix we define here is really a rank 2 tensor. Okay, and we know that using tensor makes everything convenient, because we need to make sure the equation follows the structure of scalar equals scalar, vector equals vector, and tensor equals tensor. And here we have the tensor, and we write our equation as a formula of tensor equations. Okay, that guarantees that the Lorentz boost in symmetry is preserved. Okay, anyway, so this is the T matrix and the equation from translational symmetry. Okay. And we can write down this T matrix. This T matrix contains 16 components. We can calculate the every single component using this formula, but nevertheless, it's a 4x4 matrix with 16 components. Okay. And if we write down this T matrix as a 4x4 matrix, 16 components, this equation we can write down it as a matrix formula. So the derivative is partial 0, partial 1, partial 2, and partial 3. The derivative is a row vector. The T matrix is a 4x4 matrix. T0, 0, it's super index. T0, 0, T0, 1, T0, 2, blah, 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 blah. Okay, equals to 0. Okay. 0 here means 0, 0, 0, 0. Okay, so the 0 on the right-hand side is also a vector, a 4D vector. It has 4 components. Okay, so we have equation vector equals to 0. So that is a 4D vector equation. Both sides are vectors. Okay, and we can expand this for this formula into components. Okay, for the left-hand side, a column vector, a row vector multiplied by a 4x4 matrix gives you a row vector. It has 4 components. So that's 1, 2, 3, 4, 4 components. The other side of the equation is a row vector with 4 zeros. So it should equal 0, 0, 0, 0. Okay, so this equation we obtained from translational symmetry can be written in this form. Okay. It's actually 4 equations. And these 4 equations, as you probably already noticed, that these 4 equations actually are 4 continuity equations. Okay, so every single one of them is a continuity. To realize that, we use the fact that derivative 0 is 1 over c derivative t. Derivative 1, 2, 3 is derivative x, y, and z. Okay, so we replace derivative 0, 1, 2, 3 with derivative t, derivative x, and derivative y, derivative z. Okay, and we do the same for all the 4 equations. Okay, and every single one of them is a continuity equation. Okay, so for example, the first one is partial t w plus divergence of S. W, the energy density, is actually the first guy. Okay, and and every single term here is actually one one energy current density. Okay, so this is actually I lied a little bit. So this equation, the first term, is actually W over speed of light. Okay, and every single term here is Sx over c, Sy over c, and Sz over c. Speed of light is just constant. Okay, we can multiply speed of light for every single term and cancel it. And up to speed of light, this first equation is exactly the energy conservation law we obtained in the previous lecture. Okay, and the rest 3 of these equations, every single one of them gives me a momentum conservation law. The first one is partial t, gx, the momentum density for the x component, plus divergence of t, x. equals 0. Sorry, small t. Your previous lecture, I used small t on this one. Okay, so this is a momentum density. This t sub x is a vector. It has 3 components. It's a momentum current density for the x component of momentum. Same is true for y and z. Okay, so the bottom line, this equation, this 4-dimensional formula we have here, gives me 4-dimensional energy and momentum conservation law. Okay, and in this 4D formula, energy and momentum conservation law are not independent conservation law. It is one part. It is one conservation law. Okay, this one 4-dimensional conservation law. The first component gives me energy conservation, and the rest 3 components gives me momentum conservation. Okay. And another thing, another thing we obtain from this formula is actually also quite nice. We notice that this is energy density, but more precisely energy density over speed of light. This is momentum x density. This is momentum y density. This is momentum z density. Okay. If we go back to the T matrix, we notice immediately the first row is energy density over c, momentum density around x, momentum density y, and momentum density z. Okay, so this 4x4 matrix, this energy momentum tensor, the first row is energy density and momentum density, and the rest, the 3 rows, are the currents. Okay, so these 3 are the energy currents: Sx, Sy, Sz. Actually, more precisely, divided by speed of light, Okay, and this 3 guy is the T xx, T yx, and tzx. The 3 current for the x component of momentum. And the next column is the 3 component for the current density for the y momentum, and next one is a z momentum. So this 3x3 part is the small t matrix. Okay, so let me erase everything and write it more carefully. Okay, this part is the energy and momentum density. This part is energy current S divided by speed of light. And the rest 3x3 blocks is a 3x3 T matrix we defined, small T matrix we defined last time for the momentum density. Okay, so this is how the energy and the momentum conservation law are related together as one 4D rank 2 tensor. Okay, so that's the 4D formula for the energy and momentum conservation. Okay. And once we understand the energy and momentum density, we can do a spatial integral. Okay, we can do a spatial integral for T0, 0 divided by speed of light, 0, 1 divided by speed of light, etc. Okay. And after this 4D integral, the first component gives me energy at the speed of light. The rest 3 gives me momentum x, momentum y, momentum z. And as we learned early on, this is nothing but the 4-dimensional momentum. Okay, so this is 4-dimensional momentum. So the 4-dimensional momentum is nothing but the spatial integral. Oops, I can't erase this. Okay, let me try to erase from this side. Anyway, sorry, I can't erase. Oh yeah, finally it's done. Okay, great. So the 4-dimensional energy and the momentum is just this first row, and do a spatial integral. Okay, we do a spatial integral for some volume and divided by speed of light, then we get the energy and the momentum 4D vector. Okay, and this is the 4-dimensional formula. And one more comment, same as before. The formula we discussed right now here is for just one field phi. If we have more than one field, we can do exactly the same as what we discussed in the previous lecture. If we have a bunch of fields, phi 1, phi 2, phi 3, phi 4, blah, 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 and for every single phi field, we need to do the same construction. And we add over all alpha, add over all fields. Okay? Or if you use Einstein's convention, we can write it in a more compact form like this. Alpha is a repeating index, so we need to sum over alpha. Okay? So the generic formula, the energy and the momentum tensor is defined like this. Okay, so far so good. This is a generic formula for the energy and momentum tensor. Now let's apply this technique to E and M. Okay, and let's first look at the energy conservation. Okay, The energy conservation law, the formula we are using is the first one. Okay, it's the zeros components of the energy momentum tensor. In other words, it's the first column. The first column here. Okay, that's what we are using right now. Okay, so let's look at this formula. We know that this formula corresponds to energy density and energy currents. Okay, so this is what we have. Okay. We know that T00 is energy density, okay, and the energy current density is C times T10, C times T20, C times T30. Okay, so that's energy current density. This is what we learned from the generic theory. Okay. Now let's apply this formula to E and M field. For E and M field, we know that the action of E and M field is this, E squared plus B squared. Okay. And we also know that we should not really use E and B. We need to use phi and A because phi and A has no constraints. Okay. So we should replace E field with this guy. Okay. Actually, more precisely, this is minus E, but we are doing E squared. So after the square, the minus sign that time. And for B, we replace B with a curl of A, curl of A is B. Okay. We replace E and B with phi and A. So this is my action. Okay. And in this action, we know we have 4 fields. We have one phi, one scalar field, one scalar potential, and we have 3 vector potential, AX, AY, and AZ. Okay. So we should do this construction, or this construction. And we need to do this variation for every single field and multiply it by the corresponding partial mu of the same field, that add them together, then minus I. Okay, that's what we should do. Okay. So according to this formula, this is T00, by the way. We copied the same formula from above. Okay, so for T00, we know it should look like this. And we need to do this for every single field. Okay, so this first term here actually becomes 4 terms when we apply it to E and M. Okay, this is because we have 4 fields. The first term is for scalar potential. We have scalar potential downstairs, scalar potential upstairs. Okay. You know, the downstairs and upstairs should be the same field. Scalar potential here, scalar potential here. The second term, vector potential X here, vector potential X here. Next term, vector potential Y, vector potential Y, vector potential Z, vector potential Z. Okay. So these 4 terms combined together is the first term. We do it for every single field and add them all up. And the second term, we just copy it. It's minus Lagrangian density G00. Okay, we just copy it. Okay, and then we can simplify the formula a little bit. Okay, so what we did here to simplify the formula is the following. Okay, first of all, so for partial zero is actually the speed of light times time derivative. So we should replace partial zero with time derivative. We replace partial zero with time derivative for both denominator and numerator. So that is what we have here, partial t, partial t, partial t, partial t, partial t, partial t. And another simplification is G00. G00 is a 0, 0's component of matrix tensor. For matrix tensor, 0, 0's component is 1. Okay? Matrix tensor is 1, minus 1, minus 1, minus 1. And the 0, 0's component is this guy, so it's plus 1. So we replace G00 by 1. Okay? So that's what we do here. And this whole thing is my T00, and we know T00 is the energy density. Okay? And we can calculate this and get T00. Okay? And we don't really need to calculate this because we already did the calculation. Okay? If we go to the previous weeks, the lecture notes of last week, you will notice that this formula is exactly the same formula we use to compute Hamiltonian density. It's exactly the same. And there we already showed that for the Hamiltonian density, this formula gives you E squared plus B squared plus some unimportant surface term. Okay, so those surface terms are not important because surface term it's surface. It doesn't involve anything in the bulk. If you look at if we have a really large system and look at the bulk part of the system, the surface term doesn't really matter. So the surface term becomes thrown away. And as a result, the energy density is E squared plus B squared with some coefficient epsilon 0 and mu 0. Okay, and this energy density is exactly what we learned in 505. In 505, we learned exactly the same formula and from different reasons. Okay, and here we recovered the same formula purely from symmetry. Okay, we get the action from symmetry, and then using the action by taking derivative action or Lagrangian, we get the energy density, and we get exactly the same formula. Okay, so but the bottom line, even if I don't know anything about the E and M, as long as I know the symmetry, I can come to the conclusion where E and M field carry some energy, and the energy to carry is this amount. Okay. And by the way, this is energy density, not quite energy. If you want energy, you need to do a spatial integral for some area, for some volume. Okay, so this is the energy density. And we can do the same thing for the energy current density. Okay, so the Sx, Sy, and Sz. Sx, Sy, and Sz is C times T10, C times T20, C times T30. Okay, and for T 10, 20, 30, I will call them Ti0. Okay, and I can be 1, 2, or 3. Okay, and according to the formula we have in the previous section, the Ti0 is this. Okay, and again we have 4 different fields. The field is phi, field is ax, field is ay, field is az. So this first term gives me 4 terms. We need to do this for every single field and add them all up. The second term is easy. The second term is gi0, where I is 1, 2, or 3. gi0 is 0, because my metric tensor is a diagonal matrix. I0 is off-diagonal. Off-diagonal component of this metric tensor is always 0. So the second term is just 0. We don't have a second term. So there's this energy current density is very simple. It only has this part. It don't have the Lagrangian part, Lagrangian multiply 0. Okay, and then we can calculate this quantity. Okay, so for example, T10. For T10, I should replace this I with 1. Okay, and the derivative of 1, according to the 4-dimensional formula, the derivative of 1 is partial x. So partial 1 is actually partial x. The denominator derivative becomes partial x for I equals 1. And for the numerator, the derivative 0 is 1 over c partial t. 1 over c is here, and partial t is here. I should do this for all the 4 terms. Okay. So at the end of the T10 is just this. Okay. And what is this derivative? What is this variation? Delta L, delta partial x phi. Okay. I know Lagrangian density. Lagrangian density is this guy inside of the action integral. This is Lagrangian density. I just need to do a derivative, do a variation of this. This is L, the variation of L to partial x phi. Okay, and if we can just do it as a derivative, and if we do that, we find immediately this first quantity is this guy, and this guy is nothing but minus epsilon Ex. Ex is the x component of the electric field. And I can also look at this quantity. This quantity is 0, because in the Lagrangian density, it does not contain a partial x Ax term. There is no such term. If L do not have such a term, if you take a derivative, it's 0. Okay. Similarly, for this guy, if we take the variation, it gives me this quantity. This quantity is minus Bz over mu 0. Okay. Bz is the z component of magnetic field. And finally, this last variation, if we calculate that, it is actually By over mu 0. This is y component of B field. Okay. So now we figured out what are these variations. We plug in back to this formula. Okay. So T10 is actually this guy. Okay. And this is not yet quite what we want. Okay, we need to massage this formula a little bit. To massage this formula, we replace partial t, partial ty and partial tz with this quantity. Okay. This formula comes from the fact that E equals to minus divergence of phi minus partial ta. Okay. And this formula tells me immediately, okay, if I want to know partial A, partial T, it's just minus E plus gradient of phi. Okay. So what we have is the time derivative of vector potential, time derivative of vector potential. And I can replace the time derivative of vector potential by a minus electric field. Oh, sorry, this is minus the divergence of phi. So replace time derivative of A with minus E and minus gradient of phi. You replace the Z component with minus E Z component minus gradient of phi Z component. Okay? So this is the definition of E field. Okay? If we replace these two quantities, these two time derivatives with these guys, plug them into the formula, and we get this formula. Okay? Now for this formula, we have a bunch of terms. We can massage the formula a little bit. Okay, I will combine I will take which term? These terms, and also these terms together. That's my first term. Those two terms get combined together here. Okay. And I will also combine. I will also take the time derivative of 5 terms and put it as my second term. And I have 5 terms here. Okay, the rest 2 terms I will combine them together as my last term. Okay, so I regrouped these 5 terms. Okay. And I want to argue and I want to show to you that the last 2 terms are not important at all. The last one term, this term, is not important. Sorry, the last 2 terms are not important at all. So both of these 2 terms I can get rid of. Okay. The reason we can get rid of both these 2 terms is the following. Okay. So first, let's look at this term. This term, let me copy it down here. This one, right? So for this one, I can rewrite this term and this guy. Okay. So this is the trick. Okay. The trick here is here in this term, I only have a time derivative for phi. Okay. Now I take time derivative for both E and phi. If I take time derivative for both E and phi, this time derivative may go to phi, may go to E. The part that goes to phi is what I want, but it also can go to E. So I should subtract that part of time derivative goes to E. After I subtract this, I go back to my original formula. Okay, so I can rewrite this formula as these 2 terms. And I can massage these 2 terms a little bit. It's pretty much the same thing. I didn't actually do some simplification here. So basically, I can rewrite this term as a combination of these 2 terms. Okay. And from the Maxwell's equation, okay, so this Maxwell's equation, I know that I can rewrite this time derivative of E, as curl of P minus mu 0 J. Okay. I replace this time derivative of E with this guy. Okay. Okay. Sorry, I forgot to mention one important assumption. So here we are looking at the energy and the momentum of E and the B field. Okay. We're only looking at the energy and momentum of the field. So we are assuming this region has no current and no charge. Okay. We are only looking at the E and the B fields. When this region has no energy, no current and no charge, J is 0. So there is no J. Okay. When J is 0, time derivative of E is just the curl of P. So I can replace this time derivative of E with curl of P. Okay, that's what I did here. Okay. So after I replace this time derivative of E with curl of P, this formula actually can be massaged a little bit. It becomes this guy. Okay. And this is my T10. Okay. I showed that this term is actually this guy. That's what I showed here. Okay. If I replace this second term with this guy, then it becomes this. I have one time derivative and another term, which is this guy, and I still have my last term here. Okay. And if we combine this last 2 terms together, we find that it has partial B phi and partial phi times B. Okay. When these 2 terms are combined together, it becomes a partial phi times B. So this term has derivative for B, phi don't have derivative. This term has derivative phi, B don't have derivative. When we add them together, it's a derivative of phi times B. Same is true for the other term, it's derivative of phi times B. Okay. So the last, when we combine these 2 terms together, we get this. Okay. And this term, we can rewrite it as the curl of phi and B and the x component of it. Oh, sorry, I forgot subbing x here. The x component of it. Okay. And this term is a time derivative. Okay. And oops. And if we look at this last 2 terms, immediately we notice that this last 2 term is a total derivative term. It's a total derivative. It's derivative of x times this and spatial derivative of this. Okay. And for total derivative terms, according to Stokes' theorem, when we try to do a spatial integral of T1, say 10, dx, dy, dz. Okay. The first term survives, the E cross B term survives. Okay. But the last 2 terms, they are integral of total derivatives. And for integral of derivatives, we know from Stokes' theorem, this is actually a surface integral. Okay. So these 2 last 2 terms, they only contribute to a surface integral. In other words, they are surface terms. They don't give any contribution in the bulk of the system. Because they are surface terms, don't contribute anything in the bulk. If we have a really large system and we look at the bulk, this term, this 2 term, can both be thrown away. Okay, the surface term. So this is a similar argument as we throw away in the energy density Lagrangian calculation. Sorry, Hamiltonian density calculation. In the Hamiltonian density calculation, if we go back to last week's lecture notes, you'll also see that we throw away some total derivative term. Now, this technique, this application of throwing away total derivative term in field theory is very common. It's because total derivative only contribute under the boundary. It does not contribute anything inside the system. Okay. So nevertheless, after we throw in, so this formula may look a little bit complicated, but the bottom line is we find that this last two terms doesn't matter at all. So we can throw away them. Once we throw away the last two terms, only the first term remain, and we find that the T10 is actually this guy. Okay. And we can repeat this same thing for T20 and T30. Okay. And remember the energy current density is T times speed of light. So we should multiply this guy with the speed of light, then we can find that the energy current density is actually E cross B over mu Z. Okay. This is again what we learned in 505. This is a Poynting vector. Okay. So in 505, we learned that the energy current is this guy. And in 505, we learned this from solving the Maxwell's equations and solving the relation between Maxwell's equations and the force applied to a charged particle. And here, we figure out that we don't need that knowledge at all. We don't need any detailed knowledge about E and M. As long as we know the symmetry, and we can write down the action. And as long as we write down the action, we know that the energy current density must look like this, must be this. Okay, so this is the Poynting vector. Same as what we learned in 505. We get exactly the same conclusion without using any specific knowledge about the E and M, just utilizing the symmetry. Okay, so this is energy current density. And we can do the same thing for momentum. Okay, so the momentum conservation law is the last three equation of the energy momentum tensor. Okay. So we know that the energy momentum tensor conservation law has four components. We already look at the first component, that's energy conservation. Okay, so here we will look at the next three components, that's px, py, pz conservation. Okay. So let's start from these three equations. Okay. And from these three equations, we know that this is a momentum density for x, this is a momentum density for y, this is a momentum density for z. So the momentum density is this guy. Okay, momentum density is a vector, it has three components. It is T0, 1, 0, 2, and 0, 3 divided by speed of light. And the rest part, this T11, T1, T21, and those things are the current density for momentum. Okay, so in this section, we will focus on the momentum density. Okay, we will focus on this guy. The reason we focus on momentum density is because momentum density, if we take an interval, it gives us momentum. What we want to know is what is the momentum carried by E and M field. Okay, so we will focus on these three terms. Okay, and these three terms, again, according to definition, it's this. Okay, this is what we learned in the previous section. Okay, it's a variation of Lagrangian density to the time derivative of field multiplied by the partial I derivative of the field. Okay, and again, we have actually four fields here. Okay, so we need to do this for phi, we need to do this for AX, we need to do this for AY, and we need to do this for AZ. Okay, so that's the same thing as what we learned earlier on. Okay, and again, for partial one, we replace it with partial X. We replace partial one with partial X. Okay, and the partial 0 we replace with partial T. So that's the formula we have. Okay, and again, the Lagrangian density is this. The same Lagrangian density we derive from symmetry. Okay. And then what we need to do is just calculate this variation. Okay. What is the Lagrangian density derivative of time derivative of phi? Okay. So this guy is 0. Because in the Lagrangian density, there is no time derivative of phi. If there is no time derivative of phi, this variation must be 0. Okay. And this variation, partial t of ax, it contains partial t of ax here. So if we take a derivative, this is what we get. It's minus epsilon 0 ex. Okay. We can do the same thing for the y direction and the z direction. And this is what we got. Okay. And we plug in this formula back to our T01. Okay. So back to our T01 over speed of light. This is what we got. This is what we have early on. And we substitute this one with 0. We substitute this one with minus epsilon ex. Substitute this one with minus epsilon ey, substitute this guy with minus epsilon ez, and this is what we got. Okay, so this is t0, 1 over speed of light. Okay. This is t0, 1 speed of light. Okay. And now let's play a trick. Okay. The trick I'm going to play is I'm adding one term to my t0, 1 over c. I'm adding this term. To make sure that I didn't change anything, I also minus this term. Okay, I add one term and then immediately subtract itself. Okay, so I didn't do anything. Okay, and the reason I want to do that is because after I add this term and subtract the same thing, I can massage the formula a little bit. Okay, so I can massage the formula as the following. Okay, so I will first of all, I can 1, 2, 3, 4, 5, 6, 7. So now we have 7 terms. I can combine 3 of them together, and this guy. Okay, so it's E dot that derivative of times AX. So EX partial X AX, EY partial Y AX, and EZ partial Z AX. Okay. These 3 terms combine together as this guy. Okay. And then I combine this term with this negative term, EY partial Y AX together and this guy. Okay. And I combine this term with the last term together and this guy. So I massage these 7 terms, group them into 3 groups. Okay. And this guy is nothing but EY times EZ. This guy is just a Z component of the magnetic field. Okay. This guy is again curl of A. That's a Y component of the magnetic field. Okay. So after some massage, the formula is actually very simple. Okay. And the first term, here I want to argue the first term is not important. I can throw it away. Okay. The reason I can throw the first term away is again because the first term is a total derivative. And as we mentioned earlier, if we have a total derivative, when we do spatial integral, it's just a surface contribution. A surface contribution doesn't matter, you can throw it away. Okay? And to notice that this is surface contribution, we just need to utilize this relation. Okay? We can rewrite the right-hand side of the equation, as this. Okay? So this is nothing but the derivative of 2 functions multiplied together. We have derivative of 2 functions multiplied together. We have derivative for one function, the other one without derivative, and derivative for A, and you don't have derivative, and add them together. Okay? And this term is 0 because divergence of E is charge density. Divergence of E is charge density. That's a Gauss law. And we are assuming that we don't have any charge. We are looking at the energy and the momentum of E and B field. And it's just the field. We don't want charge in this region. Okay, so this term is 0. Okay, so when this term is 0, we show immediately the right-hand side of this equation equals the left-hand side of the equation. Okay? The math may be a little bit complicated, but the bottom line is very simple. The first term is a total derivative, so you can throw it away. If we throw away the total derivative, then at the end of the day, the equation is very simple. It only has 2 terms. It only contains these 2 terms. And we can rewrite these 2 terms as E cross B and the X component of it. Okay. And we can repeat this for T20 and T30. It's the same thing, E cross B, the Y component, and E cross B, the C component. And we know that the momentum density is T over C, T over C, T over C. And we already know what T over C is. Okay, the X component, the first component is this guy, second component is this guy, third component is this guy. So we can combine them together and immediately notice that this G vector, momentum density vector, is epsilon 0 E cross B. Epsilon 0 E cross B. Okay. So momentum density is epsilon 0 E cross B. So momentum is a spatial integral of momentum density. The momentum of my system is the spatial integral of epsilon 0 E cross B. Okay, so this is a momentum density for EMM fields. Okay. Again, this is exactly what we learned in 505. In 505, we got this from Maxwell's equations, and in this lecture, we got the same thing without any specific knowledge about EMM. We only look at the symmetry, and if you know the symmetry, the momentum density must be this. Okay. So there's one more thing I want to highlight here. So the momentum density formula we learned here, the momentum density formula we learned here, G is epsilon 0 cross E cross B, is very similar to the Poynting vector, the energy density. Sorry, the energy current density we learned earlier. Okay, the momentum density and the energy current density actually satisfy a very simple relation. Okay, if we calculate their ratio is speed of light squared. In other words, G, the momentum density, is energy current density times 1 over speed of light squared. Okay. The reason is very simple. The reason is both of them are E cross B. Both of them are E cross B. Okay, both of them are E cross B. The only difference is they have slightly different coefficient. One of them has epsilon zero as coefficient. The other one has 1 over mu zero as coefficient. And this coefficient difference tells me that these two quantities are proportional to each other, and the ratio is epsilon zero mu zero. Epsilon mu zero times mu zero is speed of light squared, 1 over speed of light squared. Epsilon zero mu zero is 1 over speed of light squared. That's why we know G and S must be proportional to each other and with this ratio. Okay, so we are almost done with today's lecture. Okay, so before we finish today's lecture, let me mention one more thing. Okay, so you probably noticed that in the proof, and when we calculate energy density, momentum density, etc., we throw away something. We throw away some total derivative term. Okay? We throw away this total derivative term, and we throw away this total derivative term. We throw away this total derivative term. Okay? And we did the same thing when we calculate the energy density or the Hamiltonian density. For every single one of them, we throw away something. Okay, and these terms, this total derivative term that we throw away, actually there is a systematic reason and a systematic treatment to show what total derivative term one should throw away. Okay, so to the complete proof of that part, why do we know we need to throw away these things? The complete proof is a little bit too complicated. I will not go into details, but if you are interested in it, you can go to look at the reference book I mentioned earlier, the conformal field theory book I mentioned earlier at the beginning of today's lecture. Okay, if you look at the section 2.5, it proves to us a very interesting formula. Okay, so the TC mu nu is the same energy momentum tensor we defined in our lecture. Okay, so this book showed you that if one add this type of terms to the energy momentum tensor, and we get a new energy momentum tensor. And this new energy momentum tensor is actually as good as the old energy momentum tensor we have. It also obeys the same energy conservation. Okay, so if the partial mu of Tc is 0, partial mu of Tb is also 0. In other words, we can use this to define my energy momentum conservation law, or we can use this to define energy momentum conservation law. It doesn't really matter. Any one of them will work. And this B matrix can be any matrices, as long as it's anti-symmetric to the first two components. If I switch the first two components, I get minus sign. I can use any B, and then I can get a new definition of energy momentum tensor. And this energy momentum tensor is as good as my old energy momentum tensor. Okay, so in other words, energy momentum tensor, we have some freedom to choose what energy momentum tensor it is. We can choose any B field, any B function, any B matrix to define a new energy momentum tensor, and this new energy momentum tensor works as good as the old one. Okay, but this book also explained to us in E and M, typically there is a good choice of B. Okay, that good choice of B is this guy. We choose B as F times A. F is the rank 2 tensor of E and B fields. As we showed earlier on, E and B field forms a rank 2 tensor. Yes, it's F. Okay, and A is a vector. 4D scalar and vector potential. 4D vector. The scalar and vector potential 4D vector. When I multiply these two quantities together, F and A together, I get a B. If I use that B and use that B here to define a new energy momentum tensor, that energy momentum tensor is the best one for E and M. Okay, and the reason for that are twofold. First of all, if we choose this B, this specific B, it makes my energy momentum tensor symmetric tensor. In general, the energy momentum tensor we define is not a symmetric tensor. But if you choose the B I showed you down there, you get a symmetric tensor. And secondly, this choice makes the energy and momentum tensor, gives energy and momentum tensor a very nice connection with curvature and metric tensor. Okay, let me see where it is. It's probably down there. Oops, sorry, I can't find it. Actually, it's I can't find it. Somewhere down there. Oh, actually, it's here. Yep. So it shows that the T mu nu, if we change the metric tensor a little bit, in other words, we make our space a little bit curved, change the metric tensor a little bit, the change of action is this T. This T is the T that defines a symmetric matrix. So if we use that specific P use B to define our T, and then that T associates the change of action with change of curvature. Okay, so that is very nice because we know T is related with energy, and energy is related with mass. We actually are connecting mass with the curvature of the space. That is something very important for general relativity. So nevertheless, it is useful to use that P to modify the definition of energy and momentum principle. And that P, the contribution of that B is exactly the same as throwing away the total derivative term we were discussing here. Okay. That B actually exactly cancels this total derivative term. That is a more fundamental reason and a more mathematical reason why this total derivative term should be thrown away. Okay. Again, this is not a required part of our course. Okay. In our course, we just need to know this when we could throw away them and we get a very simple formula. But at the fundamental level, there is a reason why those terms should be thrown away. If you throw away those terms, T becomes the metric matrix, and it connects with the changing of curvature and the curved space more smoothly than the original formula we are using here. Okay, so that's some technical detail about why throwing away these total derivative terms. Okay, so let me summarize today's lecture. So in today's lecture, we first showed that the energy and momentum conservation law forms a 4D formula. Okay, and from the 4D formula, it defines for us energy density, momentum density, energy current, and momentum current. Okay, and that is generically true for any field. And then we applied the formula to E and M fields, and we showed that after throw away some total derivatives and surface term that's not important at all, we find we recovered exactly the same energy density and momentum density and energy current density we learned in 5.5. Okay, and all this knowledge are from symmetry. Okay, so as long as our universe and our E and M field follow this symmetry, it has to follow this theory, and it has to carry energy, it has to carry momentum, and energy it carry has to be E squared plus B squared, and momentum it carry has to be E cross B. Okay, and there is no freedom, and all these are totally required by symmetry. Okay. And another thing we briefly discussed in today's lecture is at the beginning of today's lecture, we mentioned that the same type of conclusion applies for any symmetry. Okay. So in this lecture, we only showed the gauge symmetry and the translational symmetry. But if you apply the same principle to other continuous symmetry, for example, rotation, you will get the corresponding continuity equation for rotation. And the rotation gives you continuity equation, and that continuity equation defines conserved quantity, and that conserved quantity is angular momentum. Okay, so for every continuous symmetry, you will get the corresponding conservation law. And the physics, many of the physics quantity like energy and momentum, all those conserved quantity actually are defined from symmetry. Okay? It's not something we randomly created. It's not some quantity we randomly created. All those quantities, as long as conserved quantity, it has a deep root to certain symmetry. And that is a generic principle. In our course, we didn't prove that generic principle. We only demonstrate two examples: gauge symmetry and the translation symmetry. If you want to learn more details, you can look at the conformal symmetry book I mentioned to you. And here, it includes a more comprehensive proof of the generic symmetry. If you have a generic symmetry, how do you write down the conservation law? And it proves that any symmetry, any continuous symmetry will give you a conservation. Okay, so that's all about today's lecture. And this part would be the last part of our discussion about symmetry and action and the conservation law and conservation quantity. And from next lecture, we'll go back to E and M and go back to the physics and E and M and study what will be the E and B field generated by a moving charged particle. Okay, I think this is a good point to stop, and I will see you next time.